Okay, we'll start. So your assignment zeros are there. They were in alphabetical order when I put them out in several piles, but the sort didn't seem to maintain itself. You all did very well, I think, on that assignment. If you have any questions, talk to TAs first, because they graded them. But I've looked through them, and I was very happy with the results, and the grades are pretty good. Grades are in Connect. Assignment 1 is due this Friday. The other thing I want to, I'll just call your attention to this panel. I think they call it Bar Talk. It's in the bar, in sub, this Thursday at 6 o'clock. There are four of us. Peter Danielson, who's a professor of ethics and medical ethics, bioethics in the Faculty of Medicine. David Poole, who's my co-author on the book, and Mike Vanderloos, who's in mechanical engineering, who builds assistive robots. We're going to talk about the ethics of AI and robotics. So if you're interested in that, come along. The other thing I wanted to say is that several students said to me after the last lecture that it was too fast. So, and I realized that I was trying to do too much in that lecture. And in particular, I didn't give you time, in the multiple choice cards questions to think about it, or even to talk to your neighbors, which is always a good idea. So I thought I'd do again a quick survey, because the first time I did the survey, on the index cards, I got more too slows than too fast. Most people were in the middle, but I think I'm speeding up a bit. I mean, we do have a lot to cover, and it does help a lot if you read the book beforehand. The sections are indicated. There's not much reading beforehand. You get a lot more out of the lectures. You'll understand them more and be able to answer the questions better if you read the material beforehand. However, having said that, let's just do a quick poll based on these colors. So red is too fast. Now this is not counting last Friday's lecture, because I acknowledge I think everyone thinks that was too fast. But just discounting that one, but before that. Just about right would be green, and too slow, you want me to speed up, would be blue. So think about that a little bit, and I'll try and get a sense of the class here. Okay, so the first thing I noticed, I don't see any blue. Well, there's the blue. Okay, he's a wise guy. He knows it all already. So, I see one blue. I see quite a few red. About 15 red, and the rest are green, which is about 65 or 70 green. Okay, so I'm going a little too fast, I would say, from that survey. And again, just keep letting me know. Tell me privately or publicly or any way you want your opinion about the course, about what we're doing, what we're not doing, we're doing too fast, too slow, whatever. I'd really like to hear it, and I'll do what I can to deal with it. Okay, so in particular today, I'm going to go over the material from the last lecture more carefully, I hope. And if there are any questions, just ask. Okay? So are there any questions before we start about anything? Yeah.
I have an admin question about the midterm. Is it going to be in class, or will we have an hour in class?
No, it'll be in class. Yeah. The question was in the midterm, it will be in class or it will be longer. It'll be in class. Any other questions? It is a bit late for a couple of reasons. Okay? So we're going to talk about CSPs again. And we're going to talk about solving them. Once we've reviewed them again, we're going to talk about how you actually solve them. And there are several methods using search. We'll find out that's not the best way to do it, and we can do much better than that. But since we already know how to do all the search things, we should start using that hammer for this particular nail. Okay? So this is sections 4.3 and 4.4. We'll do a definition, a recap, and then we'll talk about why CSPs are important. There's some very useful applications. They're very widely used. As I say, it's the basis of the iLog Cplex software used by IBM very heavily in many, many different consulting applications. And then how to solve them using generate test and graph search. So that's what we're going to do. And so in this course overview, notice that each module, here's the map for the map. For each module, we show the representation being used in the box, and then we show the reasoning technique or techniques that we're going to use on those representations. So for example, for constraint satisfaction, deterministic environment, static problem type, the representation is variables and constraints, or we called them features before, features, variables, same thing. And the way we'll solve them is initially using search, and then we'll look at the idea of art consistency, which I actually developed in the 70s, believe it or not. And then we'll combine the two. So we'll look at standard search versus CSP search. The basic idea in search is that you have this idea called state. And a state is really a black box. It's an abstract data type, if you like. I don't care how you implement it. But it should support three specific queries. Namely, can you tell me if you're a goal? Can you tell me what your successors are? Here we call it neighbors. And if applicable, if there are costs on the arcs, and B, if you have heuristics, what is your heuristic evaluation for your current state? That is, what's your estimate to goal? If it's admissible, what's your underestimate to goal? That's all you need from a state. Okay? And you could use many different data structures to implement it. And we just studied standard search using that definition of state. And we can actually, when you get into particular problems, you may have a more particular representation of state. You may use more specialized versions of search than the generic search, all those generic search algorithms we looked at in the search module. So the idea is that in each of these representation and reasoning systems, CSPs, planning, and inference, we're going to have different ideas of what the state is, what the successor function is, what the goal test is, what a solution test is, and what the heuristic function is, if there is a heuristic function. Okay? So that will show us how to specialize the search routines to those particular representation and reasoning systems.
Just a quick question on that.
Sure.
The acronym R&R?
Yeah. Representation and reasoning.
Oh, okay.
Okay? The whole course is about R&R. It's not rest and relaxation. Although for some of you it appears to be. Sorry, couldn't resist. Representation and reasoning. That's the theme of the course. How do you represent a problem? How do you reason about it? And in this general picture of the course, we show the representation here and we show the reasoning here in each of these different modules. Okay? That's a good question. So, here's the formal definition of a CSP. You need three things to formally define a CSP. You have a set of variables. We call it script V. For each variable, you'll have a domain, which we represent as DOM of V for each variable in the variable set, and a set of constraints. And we'll see later each constraint will have a scope and so on. So the simple example, here's a variable set, and we just give the variable names in the set of variables. So V1 is the one and only variable. The domain of V1 is the integers 1, 2, 3, 4. The constraints, we give them as a list of constraints by name, and then we explicitly say what the constraints are. C1 is V1 not equal to 2. C2 is V1 greater than 1. There's only one variable here, so these constraints are both unary constraints, and you can have more than one constraint on one variable here. Here's an example with two variables. two different domains. V1 is in 1, 2, 3, V2 is in 1, 2, and 3 constraints. These are all arithmetic constraints, but they can be constraints of any type as long as you can tell, given the domain values, the variables instantiated, is it true or false? That's all you need from a constraint. Having that definition, then we say a model of a CSP is an assignment of values to all of its variables that satisfies all of its constraints. Every single one of the constraints have to be satisfied. By that it means on the subset of variables that it applies to, when you test the constraint on that set of values, it returns true. Okay, so in that example we looked at, or this example here, which we looked at in the last slide, we can say there are 4 possible worlds here with V1 equal to 1, 2, 3, or 4, but only 2 of them are models because obviously if V1 is 2, this constraint fails, and if V1 is 1, this constraint fails. They all have to be satisfied, so there are exactly 2 models for this CSP where V1 is equal to 3 and V2 is equal to 4. So in this second example, get your cards ready. What are the models for this CSP? And if you want, talk to your neighbors, give you a little time to think about this, or to use a pencil and paper if you need to, or whatever. These are 4 possible worlds. There are actually more possible worlds than this for this CSP, but some of them are models and some of them are not. Could be 0 of them, 1 of them, 2 of them, 3 of them, or all 4 of them are models. Right? So how do you test to see if something's a model? Well, for each possible world, you just plug their variable values into the constraints and test the constraints one at a time. As soon as a constraint fails, you can stop with that one because it can't satisfy all of them if it doesn't satisfy any one of them. Right? So you can just test them one at a time. What do you think? Okay, so let's go through them one at a time. Here's the first one. V1 equal to 1. V2 equal to 1. Is that satisfied? C3 is false. 1 is not greater than 1. So that is not a model. If you had yellow up, it's not a model. This guy. 2 and 1. 1 is not equal to 2. That's true. 1 plus 2 is 3, which is less than 5, is true. 2 is greater than 1 is true. All 3 constraints are satisfied. This is a model. You can see that this is a model because this one is, and nothing much has changed except 3 plus 1 is 4, which is less than 5. 3 is still greater than 1. So that's also a model. But this one, V1 equal to 3, V2 equal to 2, I'm guessing that this constraint is false. Yeah, 3 plus 2 is 5, which is not less than 5. Okay? So red and green are the models. They're all possible worlds, but this first and last possible world are not models because they don't satisfy all the constraints. Okay? Questions? So, reviewing our definitions, a possible world of a CSP is an assignment of values to all of its variables. A model is an assignment of values to all of its variables that satisfies all of its constraints. So in other words, you could combine the 2 definitions and say a model is a possible world that satisfies all the constraints. Okay? So if we take this example, the same example again, how many possible worlds do I have for this CSP? 6. How do I get that? I multiply the size of the domain of V1 by the size of the domain of V2 by choosing them independently, as you do in possible worlds. right? So you just multiply the sizes of all the domains together, as we've done this many times to figure out how big a state space is. And so we can just enumerate the possible worlds. We count V1 is 1, V1 is 1 or 2, V2 is 2, 1 or 2, V is 3, 1 or 2. And we see that 2 out of the 6 possible worlds are models. Same ones we had before. We just had a couple more possible worlds here. Okay? Stop me if there are questions, otherwise I'll go too fast. It's one way of slowing me down to ask questions, right? So I have the idea that a constraint is a restriction on the values that one or more of the variables can have, and it may turn a possible world that is a model. If you throw in an extra constraint, it may suddenly make that model into not a model, because you've got another constraint to satisfy and it doesn't satisfy that one, right? So there are restrictions. And so we distinguish different kinds of constraints. Unary, where it just applies to one variable. V2 is not equal to 2. A k-ary constraint, which we usually break out into binary for 2 variables, or ternary or quaternary and so on, or k-ary. But mostly we're going to deal with binary constraints. But almost everything we say, and in the book we generalize it to k-ary constraints, but I'm not going to talk much about that. So there are various ways to specify them. We talked about this last time. You can give the extension of the constraints, which is just the set of valid domain values for the variables in the constraints. You just get listed as a table. If you've taken a relational database course, this should look very much like a relational table, a tuple, set of tuples for the constraint. Right? But we could also just have a predicate, which we call the intentional representational. You know, extension and intension. The spelling of these is important because you use an S here, not a T. So we talk about an extensional representation versus an intentional representation. So, to repeat, a possible world satisfies a set of constraints if the values of the variables involved in each constraint are consistent with that constraint. That is, they're either elements of the list of the set of valid domain values, just check and see if they're in the set of tuples, or given values to the predicate, the function, it returns true. So if I have this tuple here, v1 is 1, v2 is 1, doesn't exist in this table, so it's false. It doesn't satisfy the constraint. 3 and 1 does, because it's in the table. I didn't give this definition last time, but it's important. The scope of a constraint is the set of variables involved in the constraint. So it's some subset of the set of all variables in the CSP. It may be the whole set. It doesn't have to be a proper subset. Scope, you could have a global constraint, we call them, when it applies to the set of all variables in the CSP. But much more likely, it's on a very small subset of size 1 or 2 or 3 of the set of all variables. And we list the scope, again, as a list of the names of the variables, just as you list the set of variables in CSP as a list of the names of the variables. So this is a ternary constraint that has this scope. So how many variables in the scope of a k-ary constraint? Okay, who's buried in Grant's too? Grant. Right? The answer is in the question. We're going to look again to restrict our focus, just for this course, at finite constraint satisfaction problems. That means that A, there's a finite set of variables, and B, each variable has a finite domain. So it's not a set of reals between 0 and 1. It's not a countably infinite set, you know, the positive integers. It's a fixed number of values. Neither of these restrictions is necessary for the whole CSP framework to go through, but that's what we're going to talk about. So when we say CSP here, we really mean FCSP, or finite constraint satisfaction problem. And therefore, of course, the scope of each constraint is automatically finite because it's a subset of a finite set of variables. Okay? So again, going over the examples, We had this crossword puzzle where we had the variables are the words. So one across is one variable, one down is another variable. The domains of the English words of the correct length in the dictionary. And we only have binary constraints. Any two variables, if they intersect, must share the same letter where they intersect. And in the CSP applet, there's an applet for CSPs in the AI space, there is actually the crossword constraint is in there, so you can test and generate crosswords using the CSP applet. But if we flip the representation and flip essentially the variables and the constraints, so now the variables are the cells in our second representation. They're the individual letters. The domains are the letters of the alphabet. And now we have a whole bunch of k-ary constraints such that, this k-ary constraint there, which is what, an 8-ary constraint or whatever, is saying that all of those letters must form a valid English word. So now the constraints are in the dictionary. Right? You see that flipping. Similarly, in Sudoku, the constraints are the rows, the columns, and the boxes must all contain different numbers. The domains are 1 to 9, so they're all permutations. Each of these, or every row, every column, and every box must be a permutation of 1 to 9. So how many possible worlds are there for Sudoku? This Sudoku, I think there are about 53 empty cells for this Sudoku here. 81 minus the ones that are filled in, right? So remember, a possible world ignores the constraints, right? It just says, how many variable value combinations do I have to check to see which ones are models? We're not talking about models here, we're talking about possible worlds. Every conceivable way of filling in the Sudoku, ignoring the rules of Sudoku, right? So talk to your neighbor. Just imagine filling it in. Just say, how many ways could I fill in the Sudoku, ignoring the rules of Sudoku? If I just put in, I can only use the values 1 to 9. I could put 9 different numbers here, 9 different numbers here, 9 different numbers here. There are 53 of them, so it's 9 times 9, 53 times. Green. Right? I mean, it's easy to get confused between these two, but if you just think, how many ways could I start with the very simple case of one cell? I could fill that in 9 ways. If I had 2 cells, it would be 9 squared. If I had 3 squares, it would be 9 cubed. If I have 53 cells, it'll be 9 to the 53, okay? This is critical. We've done this a lot of times in different domains. 9 to the 53 is a large number. How large is it? I don't know. It's pretty large. Probably isn't reasonable to check every one of those possible worlds to see if it's a model, but let's ask the question, how many models are there in a typical Sudoku? One you find in the book of Sudoku puzzles at the airport. Talk to your neighbor. Do you agree with your neighbor? If you don't agree with your neighbor, show your neighbor your card and see if you agree. See if you can convince each other. Okay, having talked to your neighbor, did you manage to convince your neighbor? Put up your new answer. Hopefully it's not necessarily the same as your last answer. Great, I don't see any yellows anymore. Good. The reds convinced the yellows that typically in a Sudoku, the whole idea of a Sudoku is there's a unique solution. The solution is a set of assignments that satisfy all the constraints. That's what makes it legal. And it'd be really annoying if you bought a book of Sudoku puzzles and one of them had 2 to the 53 possible solutions. How would you know if you had the right one? Yeah.
But for a very easy Sudoku puzzle, is it possible to have more than one solution?
It's possible, yeah, but you wouldn't have 2 to the 53. This is a typical Sudoku. The ones that you're happy with typically have a unique solution because that way you're forced to backtrack enough times that you eventually get to the answer. Okay, in the answer section, they only have one answer. Okay, so we talked about scheduling problems, various constraints, so on. I won't go over that again. The n queens, no queen can attack each other. We talked about those constraints. This is roughly where we stopped last time. We may want to solve the following problems of CSP. Just the yes-no decision problem. Does a model exist for these constraints with this set of variables? Find a particular model. Find all the models. Count the number of models. Find the best model. This means we've got to measure over models. For any model, it will tell you how good it is, presumably on some scale, an integer scale or a real scale that gives you a number that tells you how good it is. You want to find the one with the best value. That gets really interesting. Or determine even higher level is some property of the variable holding in all the models. That is, in this particular, in the set of classroom schedules that satisfy all these constraints, is it true that any student has at least 20 minutes to get from one class to another? Say, you could ask that question. It would say yes or no. It would be the kind of question you'd like to ask. However, these are hard problems, okay? They're NP hard. There's no known algorithm that in every case for CSP, any CSP, will solve it in polynomial time, worst case. So you can't find such an algorithm, so don't bother looking unless you want to win the $1 million E equals NP prize. So we need to deal with it. However, there's all sorts of things we can try to do and things we will do and do. So we have these things called consistency algorithms we're going to study very shortly that are very efficient. They're low-order polynomial, like squared or cubed in the size of the problem, that hugely reduce the size of the search space. I mean, it's inherently exponential, so you can't get away from that. But you can go from 100 to some power down to 1.2 to some power of the size, and that's a huge win. And for practical problems, it may be enough to solve the problem very efficiently. Or you can restrict the kinds of problems you're going to deal with. Like we might restrict the structure of the graph. We're going to see that you can represent CSPs with graphs. The structure of the graph might be restricted, so you get special case fast algorithms. You might approximate it for that optimization problem I talked about, finding the best solution. You might say, I'd be willing to be within 50% of optimal, or even 100% of the best. If I give you that kind of sloppy best, then can you do it in polynomial time? And for many problems, you can. Okay? And in fact, even though all of this bad news about how bad all this is, in fact, on many real problems, because of the structure of constraints in real-world problems, they're not exponential. When you actually run these algorithms on, they turn out to be pretty fast on real problems. If you construct random problems, you'll find they're really bad, the algorithms. But for real problems, there's a huge structure in the locality of constraints. You might think about, say, the friendship graph in Facebook. Right? If you were running a CSP algorithm on that, you'd find huge amounts of locality. You guys are more likely to know each other than someone in Toronto, say, for example. And then this is the hierarchy of locality, which you can exploit in these algorithms. So even for very, very large problems, like the Facebook social graph, you can still get away with using these algorithms sometimes. Okay, so let's just quickly talk about why they're important. I've mentioned a little bit of this right at the beginning of the course. So for many of these problems, we can think about formal verification as being a classic application. Hardware verification, IBM, Intel, etc., all have huge groups in hardware verification because if you're fabbing a chip and you get one gate wrong, you'll scrap the whole batch and redesign and restart and pay all your customers and lose a lot of face, and they switch to another supplier. So the cost of getting it wrong in hardware is enormous. And so it's worth spending a lot in research to avoid that. So you verify them in software, and then you go to silicon. Or for software verification, it's actually harder to verify software than hardware because there are more possibilities. So only small to medium programs can be verified in using these techniques. But in the last 10 years, there's been an enormous amount of progress. And typically, you can think about CSP solvers, you can think about satisfiability solvers. Satisfiability, as we'll see, is just a special case of CSP, and yet the software tends to be specialized. You're either doing SAT solving or you're doing CSP solving, and there are competitions for both of them. So I'm assuming that you all know what propositional logic is. Is that a reasonable assumption? How many of you don't know what SAT is? How many do know what SAT is? Satisfiability. How many knows what first order, what a propositional logic formula is? How many know what CNF is? Really? You're bluffing. Come on. Well, this will look familiar to you, even if you're not willing to admit it. So we're talking about propositional logic, where you have propositional Boolean variables. And they're just like our regular variables, except we're going to write a shorthand, because they can only have two values. This is like a CSP variable x that has two values, true and false. So we'll just write little x, standing for x equal true. That's just fewer characters. That's why we do that. And negation of x, not x, for x equals false. Okay, we call these things literals. Okay, x is an atom, not x and x are both literals. So in conjunctive normal form, which is a standard form for propositional formulas, which we use often if we want two levels of gate to figure out the truth value of a propositional formula, we will put it in this standard form. And any propositional formula where, disjunction, conjunction, negation can always be put into this form. It may explode in size when you do that, but you can always do it. It has a very simple structure. It's called CNF because it's a conjunction, here are the conjunctions, the ands, of clauses. Each clause is a disjunction of literals. Okay, so I've got three clauses here. The clause is just one literal disjoined with another, and so on, right? So that's CNF form. Now, you must have seen that before. Who has not seen this before in a computer science course? Okay. Well, good, you're honest. You're willing to admit. But there's a review of this in the book and so on and so forth, but I can't spend too much time on it. So this is really a CSP. This formula is a CSP. It's got three variables, x1, x2, x3. All the variables have the domain true, false. Each clause is a constraint. There are three constraints here, and they have to all be true. Just as in any CSP, all the constraints have to be satisfied. So you can see this is just a very special purpose CSP. Right? There's the CSP. I've written out the three clauses separately. And you know the truth tables for disjunction. So you know when each of these are true. Like this clause is only false in one case, right? When x1, x2, and x3 are all false. Otherwise, it's always true for all the 7 other cases, right? So we could say, for this formula, how many possible worlds are there? Eight. Right? There are 8 possible worlds because there are 3 variables. So you can count in binary. Each one of those, 0, 0, 0 is one possible world. 0, 0, 1 is another one. Okay? So there are 8 possible worlds. They're not all models. We could check them one by one, but we won't. But you could. Here's a model. If x1 is true, x2 is false, and x3 is true, we know it satisfies that one, because they're not all false. Satisfies this one because, for example, this not false is true, so that makes this one true. And here not false is true, which makes this one true. So this is indeed a model, as claimed. And we could check all the possible worlds to see which ones are models. Okay, so SAT, which is the problem that I just defined, the SAT is the problem of finding the number or the existence of models in a CNF formula. If it's 3 SAT, the restriction of 3 SAT is that is equal to sat with at most 3 literals per clause. I don't think I wrote this on the slide. And it's a famous problem in computer science because it was the first problem that Steve Cook in 1973 showed to be NP complete, finding whether or not the 3-sat problem is NP hard. It's NP complete in that if you had a polynomial algorithm for 3-sat for finding models of this formula, then you'd have polynomial algorithms for every other problem in NP, which we believe is not true. So even this very simplification of CSPs is NP complete. Okay? But that's the one that's often used for these verification problems that I was talking about. Finding bugs in Windows, verifying computer chips, IBM and Intel and so on are big players in that market. There's a big market in SAT solvers. In fact, UBC is one of the best places to do this work. So it's amazing how big SAT problems can be solved. Even as I say, these are officially hard. You shouldn't be able to do this. In fact, you can, with hundreds of thousands of variables, millions of constraints, you can get runtime in the order of a second. And that's because of the thing that I said, namely, these are real problems. They're real hardware, which has locality. The constraints tend to be clustered locally at different levels in the hierarchy and so on. Same with software. That's why you can often run them fast. But there's still many classes of instance where these current algorithms fail. And just to pick an example, because it's the UBC example, Zhu, Hutter, Holger Hoos, and Kevin Leighton Brown wrote this program called SATzilla, which combines, it's a monster solver, got the name, combines many other different solvers. It's the idea of an algorithm portfolio. You know, you try and learn, and they use learning to figure out, for all these different solvers out there you could possibly use, using the characteristics of the problem, which solvers are likely to work best on this problem. Okay, it's the idea of an algorithm portfolio, which was developed by them. Here, very cool. So, questions so far? Yeah.
So you said that any SAT problem can be considered as a
CSP, yeah.
Yes. Is it true the other way around?
Any CSP is a SAT problem? No, because it's more general. So, you know, instead of, this is the set of all CSPs. This is the set of SAT. All SATs are CSPs, but not all CSPs are SAT. Because we've taken the CSP definition and said you've got variables and domains and so on, and specialized it. We've said all the variables are have binary domains.
Oh,
okay? Right? There is a way, it gets technical, but there is a way to take any CSP problem and turn it into a much larger SAT problem. So you can't actually go the other way. But if you just take the simple definitions that we had, it's like that. Okay? Any other questions? Okay. So, how do you solve a CSP? And we've talked about CSPs. So what's the dumbest possible algorithm? Just generate every possible world and test it to see if it's a model. So you're guaranteed to be worst case exponential. You're guaranteed to be best case exponential if you do that, right? But, you know, it's nice to know there is an algorithm to solving the problem, and then we try and do better. So we call this generate and test. It used to be called the British Museum algorithm, because you sort of run around the British Museum and look. If you're looking for something in the British Museum, you just run around and look at every exhibit till you find what you want. Generate and test just means we're going to generate every possible world and then test it and throw it away if it's not a model. Okay, so the possible worlds are the cross products of the domains, Cartesian cross products. And so we'll generate possible worlds one at a time and test them one at a time. So for A in the domain of, if we have 3 variables, A, B, C, for each A and A, B and B, C and C, if they satisfy all the constraints, return it. That's the algorithm. Done. right? Say. Very simple, very dumb. So, get out your cards. How bad is it? When we're evaluating the complexity of CSP algorithms, we typically use the number of constraint checks, because that's usually a measure of runtime. So how many constraint checks are is what we mean by complexity here. Because constraint check is typically a unit operation. You can look it up in a table, call a function. Right? So talk to your neighbor. Show your neighbor your card. Once you figure out your color, show your neighbor the color. If you don't agree, have a little argument. This one. Okay, so show your cards now. Poker, show your cards. Okay, we're getting lots of greens, which is great. So, yeah, there was some divergence initially, but again, we know there are d to the k possible worlds, because if there were one variable, there would be d worlds. If there were two variables, there would be d squared. If there were k variables, there are d to the k possible worlds. And for each possible world, at the worst case, I mean, if you're lucky, the first one will fail if you're going to fail them. But if at the worst case, you have to make sure every constraint is true. So this is all worst case. So for each world, d to k, you have to check k constraints. So you multiply these two numbers together. I mean, this is just sort of elementary time complexity analysis, right? Question?
Do we assume that C is a constant so the bigger the you wrote it?
C is a constant, but it could be a very large number. I mean, when you're evaluating the time complexity of an algorithm on a problem, you want to parameterize in terms of the size of the problem, right? So, yeah, this d to the k will dominate, but C could be 1 million or 100 million. You know, so we need to know as the constraint problem gets bigger, if I double the number of constraints, what will happen to runtime? So this will tell us that if you just double the number of constraints, the runtime will double. Okay? Yeah.
What does C have to be a constant? For example, if you say you can't, there can be any replicates. Then you got to check every single thing you check before to see if that is the same thing that you.
So it's a constant because we have a particular CSP that we're solving, right? It has a particular set of k. K is a number. It's a set that there are that many variables. D is the size of the domain for each variable. We assume the worst case they're all the same size d. And there are C constraints. C could be 1 million, say, or whatever. So you've got a particular problem you're trying to solve. How fast will this algorithm run on that problem? So C is fixed. Once you've decided on the problem you're solving, C is fixed.
For example, if you say a number cannot appear 2 times of above, so after you check a number, each time you finish checking a number, you're adding a new constraint that is the new number you're checking cannot be same as the number you previously checked. So
no, in order to have a CSP, you can't dynamically create constraints at runtime, which is what you're doing. You have to tell me, to specify the CSP, you have to tell me ahead of time, what are the variables, what are the domains, what are the constraints? And that's fixed. You have to tell me, you know, there are 33 variables and constraint number 61 involves variables 6 and 7. And that's it. It's fixed. Okay? If you want to solve the problem you're talking about, that's outside the domain of CSPs. If you're dynamic, I mean, there are people who do dynamically check constraints, and there's something called dynamic constraint satisfaction where the constraints change as you're trying to solve the problem, right? I mean, that's like the FedEx truck who gets his initial assignment of packages and delivery addresses, and as it's executing, someone says, okay, I don't want that package to go there, I want it to go there. You've changed the constraint in the middle, actually, not even when you're solving the problem, when you're executing the solution. We're not dealing with dynamic CSPs at this point. Okay? Any other questions? It's good questions. They're good questions, all of them. Okay. So, How else could you do a little better than generate and test? Well, you exploit the locality of the constraints, okay? And use something like the search techniques we've already used to do better. So here's one way. We've got two different formulations for CSPs as a search problem. Here's one. A state is a partial assignment of values to variables. So we have some set of variables with assignments and the rest of the variables aren't yet assigned. That's a state, okay? Our start state is having no variables assigned values. And you generate the successor of the start state by assigning the next variable a value. And in this version, we're going to have a fixed total order of the variables. Ahead of time, I'll tell you V1 is first, V2 is second, Vn is last. Okay? So if, for example, a state has assigned values to the first k variables, like here, V1 up to Vk all have values, the neighbors of this node are the set of all nodes where you've assigned the next variable, Vk plus 1 values, for each x in the domain of that variable. So we're just sort of one by one assigning a value to a new variable until we run out of variables, and then we've got a total assignment, right? So the goal state is a complete set of assignments of values to variables that satisfy all the constraints. The goal states are the models in this formula. What we're doing is just taking our standard search formulation and deciding what is the state, what's the start state, what's the successor function, what's the goal state. We have no cost function because it's just unit cost in all the arcs. And we don't care actually about the path even. Before we cared about the path, how we got there. Now we don't care. We just care what goal state are we in, what model do we have. Okay, the solution is the assignment. The path doesn't matter. So given that, what search algorithm would you use? Think about that. Come to an answer, and then talk to your neighbor and see if you agree. And think about what it is about CSPs that would allow us to use one of these search algorithms, right? And the key is in the idea of the locality of the constraints. Typically, the constraints will involve a small number of variables, right? And they all have to be satisfied. Those are the two clues you need to know to answer this question. So you got 3 answers? It says which one? Most appropriate. You've got to place your bets on one answer. You can't hedge all your bets here. We have no heuristic function. I didn't give you a heuristic function. That kind of rules out A star, right? Think again, if you had A star. I don't care about the cost of the arcs. I don't care about the path length. I don't care about the cost of the arcs, so it's not least cost first. Doesn't really leave a lot out, except maybe none, right? The key is the locality. If I've just considered 2 variables, I've assigned them values, I can check any constraint that involves them right away. And if it doesn't return true, I can forget about going any further. I can fail at this point. And depth first search is the way to do that, right? Because I can fail now and cut off a huge, humongous search tree below there, never look at it, because it has to satisfy all the constraints. Okay, so as I said, the path to goal is not important. The heuristic function is none. All the goals are at the same depth. They're at depth n, right? All at the same level. So, explore the search space via depth first search, but evaluate each constraint as soon as all of its variables are bound. Any partial assignment that doesn't satisfy that constraint can just prune. Just cut it right off there. Okay, for a big win. And that's what we call a backtracking algorithm. So, we'll pick that up next time.